For 4.5 billion years, Earth has endured. It has weathered cosmic bombardments, migrating continents, boiling furnaces, and frozen deserts. Yet life has persisted, stubborn, adaptable, improbable. From the fragile filament of a single-celled organism to the complex ecosystems that have painted the planet green and blue, our world has seemed, in many ways, indestructible. And yet, in the span of a single human lifetime, we have learned enough physics, built machines of staggering power, and coaxed technologies from theory into reality that the old stories about inevitability must be re-examined. What would it actually take to destroy planet Earth? That is the central, unsettling question we'll unpack, not as a fever dream of science fiction, but as a catalog of physical possibilities, some obeying the laws of nature as we currently understand them, some requiring us to bend those laws into unlikely new forms. We will travel from the scale of the subatomic to the scale of galaxies, examining scenarios that range from the microscopic to the planetary, from the slow and inevitable to the spectacular and sudden. Along the way, we'll ask a deeper question, too. How much of this is purely hypothetical? How much is technically feasible? And how much is already within our reach, intentionally or otherwise? Imagine a marble-sized object with the gravity of the world's mass. Imagine an invisible, ravenous well that not even light can escape. Picture the sun, our life-giver, turned from a steady companion into an oven that bakes oceans away. Think of machines that replicate until they consume the rocks under our feet, or of stores of antimatter so vast that a single release unthreads matter itself. Each image is dramatic, and each corresponds to a real set of physical principles: black holes and tidal gravity, stellar evolution, impact dynamics, exponential replication, annihilation energy. Some of these are ancient threats the cosmos posed long before life appeared. Some are emergent risks that accompany our growing technological competence. We begin with scale. To obliterate a planet is not merely to harm it. It is to break the gravitational binding that keeps rock and metal coalesced, to unbind the mass so that you no longer have a world, but an unmoored spray of debris. That requires energy on an almost incomprehensible scale. The sun pours out energy in quantities that dwarf human industry. A single week of that output is, in some contexts, the yardstick for the energy you would need to tear Earth apart. Yet energy alone is not the whole story. How it is delivered, concentrated at a point, distributed as a tide, or applied over millions of years matters enormously. A focused event, like a collision with an object the size of Mars, can vaporize and eject huge fractions of the crust. A gradual reconfiguration of orbital energy can, over millennia, nudge a planet into a fatal proximity to its star. And there is danger on both ends of scale. At the subatomic frontier, particle colliders reproduce conditions of extreme energy in miniature. The idea that we might accidentally create a tiny black hole that swallows the world is more dramatic than practical. Microscopic black holes, if produced, are expected to evaporate almost instantly. But the concept forces us to confront a hard truth. Our pursuit of fundamental knowledge can edge us toward phenomena whose global implications we barely understand. At the other extreme, the solar system is full of massive, cold bodies, asteroids, comets, even planetary embryos. A direct hit from something the size of a small planet is physically capable of shattering the Earth. Historically, the cosmos has already demonstrated this. The collision that likely formed the Moon was a planet-scale cataclysm. That same mechanism, deliberately replicated or coincidentally reproduced, could end us. There are also avenues that feel eerily domestic. technologies we invent for good, swarm robotics, nanofabrication, precision propulsion, could, in pathological circumstances, scale into planetary threats. Self-replicating machines that harvest raw materials to build copies of themselves begin as clever tools and, if unchecked, could transform entire mineral reservoirs into machinery. Antimatter sits on the other side of the ledger, a beautifully symmetric property of particles that, when brought together with ordinary matter, annihilates into pure energy. The physics is clean. The engineering is brutal. Enough antimatter released in the wrong place would be catastrophic. The real obstacle is producing and containing such quantities. Throughout this series, we will be rigorous and skeptical. For each dramatic image I've painted, the marble black hole, the plunging Earth, the mushroom cloud annihilation, the ravenous robot swarm, we will estimate scales, evaluate feasibility, and separate poetic possibility from plausible threat. We will speak with the scientists who specialize in planetary impacts, stellar evolution, particle physics, robotics, and planetary dynamics. We will reconstruct ancient events recorded in the geological archive, the scars of impact craters, the isotopic signatures that reveal how water arrived here, and use them as laboratories for what might happen again. But this will not be mere cataloging. The deeper story is about agency, the difference between natural cosmic forces and risks that are a product of intentional or accidental human action. Nature can end civilizations without meaning to. Human technology introduces new vectors where intention, error, or malicious use matter. Understanding which is which shapes how we prioritize defense, how we legislate and govern, and how we steward knowledge that could be weaponized. In the end, the question, can we destroy the Earth, is both terrifying and clarifying. It forces us to quantify our reach and to reckon with our responsibility. It asks whether the planet, a system so robust it has persisted through incomprehensible violence, can be undone by processes that range from the astronomical to the minutely engineered. And it presses us to decide how we will behave with the power we already hold and the power we will inevitably gain. So let us begin. We will start where the universe itself leaves fingerprints, the cratered scars, the isotopes trapped in ancient minerals, the faint whispers of gravitational theory. From there, we will move outward and inward, exploring the machinery of catastrophe and the measures humanity could take to prevent it. By the time we finish, you should have an uneasy but precise picture of what stands between Earth and oblivion, and what stands between humanity and the choices that could render that picture real. Part 1. The First Threat. A Hole in Space. It begins not with an explosion, but with silence, a gap, a distortion, a missing piece of reality. Astronomers at several observatories across the world start reporting something strange. In the vast field of the night sky, where millions of stars have always burned in steady patterns, a small patch has gone dark. It isn't a cloud, nor dust, nor an error in the telescope's optics. The stars simply vanish when viewed through this region, as if light itself is being swallowed. At first, it's written off as a software glitch. The European Southern Observatory rechecks its sensors, while a team at Caltech recalibrates its lenses. But the data keeps coming back the same. Over several nights, the same coordinates show a progressive dimming of background starlight, a signature no one wants to believe. A black hole. The words carry weight, even among scientists who speak of neutron stars and quasars with casual ease. Black holes are supposed to stay far from home, cosmic leftovers of dead suns, found in the deep recesses of galaxies. Yet the calculations suggest this one is moving, slowly but unmistakably, toward our solar system. At first, it sounds like a headline designed to panic. News channels pick it up with dramatic music and simulations of Earth being swallowed whole. The scientific community, however, is careful. We have no confirmation of proximity, says Dr. Clifford Johnson from the University of Southern California. At this stage, all we know is that something with extraordinary gravity is warping light across a measurable section of space. But within days, the gravitational lensing data speaks for itself. Stars near the region are shifting position, not because they are moving, but because their light is bending. Space itself is curving inward, and the curve is deepening. What the world doesn't yet know is that this kind of detection isn't new. Theorists have long warned that the Milky Way may contain millions of black holes, relics of massive stars that collapsed billions of years ago. Most drift harmlessly in the void, but if even one of them, a black hole of several solar masses, were to pass within a few light years of Earth, the consequences would be catastrophic. For weeks, observatories around the planet turned their telescopes toward the invisible intruder. The Hubble Space Telescope, then the newer James Webb, began scanning in infrared to look for heat signatures. They find none. The object emits nothing, but its gravitational pull is undeniable. Using the shift in background starlight, NASA scientists estimate its mass, 3 times that of the Sun. That number freezes the room. A stellar mass black hole, compacted into a sphere barely 18 kilometers wide, is now traveling through interstellar space at 40 kilometers per second, aimed roughly in our direction. Not directly at Earth, but close enough that its tidal influence could disrupt the orbits of the outer planets. If it grazes the Kuiper Belt, it could fling comets inward, transforming the solar system into a shooting gallery. Dr. Lawrence Krauss, a cosmologist known for his blunt realism, summarizes the threat in a late-night interview. Think of the solar system as a ballet of gravity. Everything moves in balance. But if a new dancer, especially one as massive as a black hole, enters the stage, the choreography collapses. Planets could shift, orbits could destabilize. Even if it never touches Earth, it could send enough debris our way to make extinction inevitable. The public reaction is divided. Conspiracy forums flood with talk of fabricated science and controlled panic. Social media spins with images of black marbles devouring the world. Governments issue careful statements denying any immediate danger. But deep beneath the headlines, the calculations continue. The object's trajectory will bring it within 200 astronomical units of Earth, closer than the Oort cloud, within a few centuries. For astronomers, that is practically tomorrow. Meanwhile, something stranger begins to happen. Subtle variations in the orbits of distant probes, Voyager 1 and 2, still whispering from the edge of the heliosphere, no longer match predictions. Their trajectories are bending infinitesimally toward the same direction as the anomaly. NASA engineers initially blame aging hardware or signal interference, but as more data arrives, the pattern is undeniable. The probes are being pulled. And so, a hypothesis becomes a possibility, and a possibility becomes a warning. For the first time, humanity faces a real physical reminder that the universe is not benign. Black holes are not just equations written in chalk. They are predators of matter, invisible and unstoppable, and one of them may be heading this way. Still, the question remains, what would actually happen if such an object reached us? Would Earth be torn apart instantly, or stretched into oblivion by tides of gravity? Could our instruments detect it before it crossed the invisible threshold known as the event horizon? And more chillingly, could we ever survive such an encounter? To answer those questions, we must first understand what a black hole really is. Not merely an object, but a region of space-time where gravity conquers everything, including light. To approach it is to approach the edge of physics itself. Part 2, Gravity Unbound, the Science of Black Holes. When Einstein first described gravity not as a force, but as the curvature of space-time, even he could barely imagine the extremes his equations implied. The idea that mass could bend the geometry of the universe around it was radical enough. But the mathematics offered something even more startling, a prediction that, under certain conditions, matter could collapse so completely that the curvature became infinite. The result was a singularity, a point where the known laws of physics disintegrate. Today we call that point the heart of a black hole. Around it lies the event horizon, the boundary beyond which escape is impossible. The name is literal. No event inside that horizon can ever influence the outside universe. Beyond it, time and space switch roles. To move forward in time is to move inevitably inward. Once you cross the horizon, every possible path through space-time leads to the same destination, the singularity. It's easy to treat these words as abstractions, but in recent decades, astronomers have come as close as physics allows to confirming them as fact. The detection of gravitational waves in 2015 was the first direct proof that black holes collide and merge, sending ripples through space-time itself. The Event Horizon Telescope's image of the black hole in the galaxy M87 gave us the first visible evidence of the shadow a black hole casts. A perfect dark circle ringed by the light of doomed photons, orbiting at nearly the speed of light. For all this evidence, though, the danger remains theoretical until you start scaling the numbers. A black hole with the mass of our Sun would be about 3 kilometers wide. Increase the mass to that of the Earth, and you compress all of our planet's material into a sphere the size of a marble. Compress 3 suns, and you have a gravitational engine powerful enough to swallow worlds whole. The escape velocity at its horizon exceeds 300,000 kilometers per second, the speed of light. To visualize what happens near such an object, think of a waterfall. Space itself is like the water, flowing downward faster and faster toward the abyss. Far from the hole, light can still paddle upstream. Its motion through space counteracts the flow. Closer in, the current strengthens until not even light can resist. The point where that happens is the event horizon, the cosmic equivalent of the lip of Niagara Falls. For an unlucky planet wandering too close, the encounter unfolds in stages. Long before the horizon itself, the black hole's tidal forces begin their work. The side of the planet nearer to the hole feels a stronger pull than the far side, stretching it into an ellipsoid. The crust cracks. Oceans heave upward in mile-high tides. The gravitational gradient intensifies exponentially, and soon the planet's cohesion gives way. Rock, iron, and atmosphere stream outward in spiraling ribbons of debris. Astronomers call the process spaghettification. From a distance, it's oddly beautiful. The torn remains of the planet form an accretion disk, glowing with X-rays as they spiral toward oblivion. The light, curved by gravity, forms a halo, a mirage of a world's final moments. But perhaps the most haunting thought is that, for an observer falling into the hole, time itself changes character. From their perspective, the fall takes seconds. To an outside observer, it appears to slow infinitely, freezing at the horizon. The doomed planet and everything on it would appear to hang motionless on the brink of darkness, light stretched into longer and longer wavelengths until it fades from view. And yet, paradoxically, the black hole itself is not eternal. Stephen Hawking's work showed that black holes can evaporate very slowly through quantum effects near the horizon. The process is so faint that a stellar black hole would take far longer than the age of the universe to disappear. Still, the idea reveals a profound truth. Even the most perfect destroyer decays eventually. Could humans ever create one? That question has haunted particle physics for decades. In theory, a collision of particles at sufficient energy density could compress matter into a microscopic black hole. Experiments at the Large Hadron Collider flirt with those energies, but every serious analysis concludes that any such black holes would evaporate instantly. Nature herself produces far higher energies in cosmic ray collisions every day, and Earth still exists. But the fear remains powerful because it touches on something primal, the idea of building a machine so powerful it unravels the ground beneath us. For now, the cosmic black holes drifting through the galaxy pose a more credible threat. Astronomers estimate there are at least 10 million of them in the Milky Way, most invisible unless they happen to feed on nearby matter. If one of them were wandering near our system, we might not see it until it began to disturb the orbits of distant comets. If or when that happens, what could we do? Nothing. No weapon or propulsion system could push back against gravity itself. Once the trajectory is set, the encounter becomes a question of celestial mechanics, not technology. At best, we might observe the end of our planet as it's stretched into dust. Still, the scenario reveals something deeper about destruction itself. Total annihilation doesn't always come from malice or accident. Sometimes it's written into the fabric of the universe. Black holes are nature's proof that creation and destruction are two faces of the same geometry. But there are other, more human ways to end the world, ways that don't require the collapse of stars. The cosmos may destroy by gravity, but humans can destroy by curiosity. And so, our story turns inward again, to laboratories buried beneath mountains, where machines the size of cities smash atoms together at nearly the speed of light. These are the modern cathedrals of physics, and some scientists quietly wonder whether, in our pursuit of knowledge, we might one day build the very engine of our own undoing. Part 3. The machine that could eat the world. The Collider Paradox. Beneath the green hills straddling the border of Switzerland and France lies one of humanity's most ambitious creations. A ring of superconducting magnets stretching 27 kilometers in circumference, buried deep under the surface of the Earth. The Large Hadron Collider is an engineering miracle, a machine designed to recreate the first microseconds of the universe. Inside its tunnels, protons are accelerated to 99.99999% the speed of light before being slammed together in bursts of unimaginable energy. When it was first switched on, it was hailed as the pinnacle of scientific curiosity, the place where physicists might discover the secrets of existence itself, the Higgs boson, the nature of dark matter, perhaps even the unification of quantum mechanics and gravity. But outside the scientific community, another story was brewing. What if, a few voices asked, those collisions could create something uncontrollable? It was an innocent question, but one that spiraled into global anxiety. The fear was simple, dramatic, and terrifying. Could the LHC create a black hole that would swallow the Earth? Officially, the answer was no. Before the collider's first beams ever circulated, the European Organization for Nuclear Research, CERN, commissioned an independent safety review. The conclusion was unequivocal. The energies achievable in the collider, while immense by human standards, were minuscule compared to natural cosmic ray collisions that strike our atmosphere every second. If microscopic black holes could be made that easily, the universe would have long since devoured itself. Still, the thought persisted. There was something intoxicating about it. The idea that, in our quest to understand the building blocks of matter, we might accidentally trigger an event that ends all matter entirely. In physics, speculation is part of progress. Some theories in higher dimensional space suggest that if extraspatial dimensions exist, gravity might become much stronger at small scales. In such a universe, tiny black holes could form in high-energy collisions. Yet according to Hawking radiation theory, those black holes would evaporate almost instantly, a subatomic burst of particles gone before they could affect even a single atom around them. But for all the reassurance of the math, the collider itself inspires awe. When viewed from inside, its tunnel hums like a heartbeat. The magnets, cooled to colder than outer space, guide beams of light-speed protons through vacuum pipes thinner than human hair. At the moment of collision, the energies released are small in scale but enormous in precision, enough to probe the fabric of space-time itself. Dr. Phil Plait, an astronomer who has spent years debunking apocalyptic claims, once described the fear this way: "It's not the math people are scared of. It's the feeling that we've built something we don't fully understand, and that nature might punish us for our arrogance." It's an ancient sentiment, older than physics itself. Every great leap forward carries a shadow, the notion that knowledge comes with a price. When humanity first split the atom, the chain reaction that powered cities could also level them. When we began sequencing genes, the same code that could cure disease could also be rewritten in terrifying ways. And so, the collider becomes a metaphor, our desire to see the beginning of time colliding with our fear of ending it. In truth, the worst the LHC can do is generate headlines, not singularities. Its collisions produce fleeting particles that decay before they cross even a few millimeters. But the idea of an engine that could eat the world lingers, because it forces us to confront how small the barrier can be between creation and destruction. Physicist and cosmologist Lawrence Krauss once performed a thought experiment. Imagine the energy released in the collider's most powerful collision. Now imagine concentrating that same energy not in a particle, but in a sphere the size of a planet's core. To create a black hole massive enough to consume Earth, you would need the energy the sun emits in an entire week. Humanity's total energy output since the dawn of civilization wouldn't even register on that scale. So, no, the collider won't destroy the planet, but it gives us the vocabulary to imagine what could. And here, imagination becomes the seed of new terror. If gravity itself is beyond our reach, perhaps there are other forces that could unmake the world, not through collapse, but through combustion. Energy, after all, can destroy as effectively as gravity can devour. That brings us to the next frontier, a substance so potent that a few grams could erase a city, and a mountain's worth could vaporize a planet. It's not fiction. It's antimatter, the mirror image of reality itself. Part 4, the annihilation equation, how antimatter could unmake the world. Deep in a vacuum chamber at CERN, a single speck of invisible dust is suspended in midair, not by wires or magnets, but by the careful balance of electromagnetic fields. It's not ordinary matter, it's antimatter, the most dangerous, elusive, and symmetrical form of energy ever discovered. For every particle that makes up our universe, electrons, protons, neutrons, there exists an opposite twin. Same mass, same spin, but opposite charge. Bring the two together and the result is annihilation. The particles don't explode, they cease to exist, converting every gram of mass into pure energy according to Einstein's most famous equation. E equals mc squared. That single equation holds the key to unimaginable power. 1 gram of antimatter colliding with 1 gram of matter would release energy equivalent to roughly 43 kilotons of TNT, about 3 times the bomb that leveled Hiroshima. A kilogram? The yield would rival every nuclear weapon ever detonated on Earth. It's not hard to see why physicists call it the most efficient explosive in the universe. But here's the twist. Antimatter isn't just theoretical. We've made it. In the same particle colliders that probe the subatomic world, scientists have created antiprotons, positrons, and even anti-hydrogen atoms, storing them for fractions of a second in electromagnetic traps. Those tiny quantities, nanograms at most, are harmless in isolation, but together they whisper a question that keeps certain physicists awake at night. What if we could make more? The 20th century's nuclear revolution was born from kilograms of uranium and plutonium. The antimatter revolution, if it ever arrived, would require only milligrams, 1,000 times less mass for 1,000 times more power. But therein lies the challenge. Creating antimatter is prohibitively difficult. In current colliders, for every 1 antiproton produced, 1,000,000 protons vanish as wasted energy. Storing even a few nanograms requires vacuum conditions better than those in interstellar space, and magnetic fields strong enough to keep the antimatter from touching ordinary matter, because contact means instant annihilation. Dr. Lawrence Krauss puts it bluntly. If you dropped a single speck of antimatter on your desk, it would never touch the surface. The air molecules alone would trigger an explosion that vaporizes the lab and everything in it. It's that instability that both fascinates and terrifies physicists. A bomb made of antimatter wouldn't just burn, it would unmake. No radiation, no lingering fallout, no half-life. Just the complete conversion of mass into energy in a flash of gamma rays, brighter than the sun. So what would it take to build an antimatter bomb capable of destroying Earth? Let's do the math. The planet's gravitational binding energy, the energy required to overcome the gravity that holds it together, is approximately 2.5 times 10^32 joules. That's an impossible number to grasp, but if we translate it, you'd need about 2.5 trillion tons of antimatter to tear Earth apart completely. For perspective, that's roughly the mass of Mount Everest multiplied by 1,000, all made of antimatter, suspended in magnetic containment and delivered precisely to the planet's core. The thought experiment gets worse. To maximize destruction, the bomb would need to detonate near the planet's center, ensuring the energy radiates evenly in all directions. But the deepest hole humanity has ever drilled, the Kola super deep borehole in Russia, only reaches 12 kilometers, barely scratching Earth's crest. The core lies nearly 4,000 miles down. So yes, it's possible in principle, but the engineering is absurd. It would take more energy to produce that much antimatter than the sun emits in weeks. At our current rate of production, a few nanograms per year, It would take longer than the age of the universe to stockpile enough to matter. And yet, the idea persists because it embodies the perfect paradox. The same technology we use to understand creation could, in theory, end it. A team of engineers once simulated what a smaller-scale antimatter detonation would look like, say 1 kilogram. The result was sobering: an explosion large enough to obliterate a major city and melt a significant section of Earth's crust. If somehow contained beneath the surface, the heat and pressure would trigger global earthquakes and possibly rupture the mantle. But here's the irony. Even if we could produce the material, we couldn't hold it. Antimatter must never touch matter, meaning it needs to hover in a perfect electromagnetic prison. The slightest power outage, a single misalignment, and the containment field collapses. The antimatter touches the walls, and the entire device vanishes in a burst of gamma radiation. It's both the most perfect and the most impractical weapon ever imagined. And yet, nature herself once played with this symmetry. In the earliest moments of the Big Bang, matter and antimatter were created in almost equal amounts. For reasons still mysterious, matter won by 1 part in a billion. That imbalance is why anything exists at all: planets, stars, and life. If the scales had been perfectly balanced, the universe would have annihilated itself into pure light. That cosmic accident is the reason we're here to even contemplate our own destruction. So perhaps antimatter isn't our most realistic planetary threat. It's a mirror, a thought experiment in the fragility of existence. But if annihilation isn't efficient enough, there are other, more immediate ways to end the world. Imagine moving an entire planet, not by explosion, but by precision, gently altering its orbit until it spirals into the sun. The technology to do this exists in its infancy, and the physics behind it is terrifyingly simple. Part 5: The Fall into Fire. How to drop a planet into the sun. The idea sounds almost laughably cinematic. Take a slow, steady hand and push Earth toward its doom. No dramatic singularities, no instant annihilation, just a patient, relentless theft of orbital energy until our world spirals inward, bakes, and finally unravels in a furnace. It's not magic, it's gravity and momentum, the same tidy mechanics engineers use to fling probes to the outer planets. In the right hands, and with enough time and mass to play with, you can change a planet's destiny. Start with a simple principle every spacecraft engineer knows: the gravity assist. A probe aimed past a planet can steal a fraction of that planet's orbital energy and use it to boost itself outward. You've seen the result in headlines: probes launched into the outer solar system that owe their trajectories to carefully timed flybys of Venus, Earth, and Jupiter. Energy is transferred locally and predictably. Momentum is conserved. The astronautical trick is that you don't need rockets powerful enough to push a planet. You can cheat by borrowing energy from other bodies. Now invert the trick. Instead of stealing energy to push a spacecraft outward, design a sequence of encounters that steals energy from Earth itself and dumps it elsewhere, into another planet, into an asteroid, into Jupiter's deep gravity well. Each encounter is tiny, but over thousands or millions of repetitions, those tiny losses add up. The planet's orbital speed decreases, the ellipse of its orbit shifts inward, and the sun grows larger in the sky. How could such a process be executed at scale? The engineering concept that keeps reappearing in thought experiments is deceptively simple. Use asteroids as the conveyor belt. Capture a large rock, maybe a kilometer or several kilometers across, and adjust its orbit with robotic propulsion so that it performs a close flyby of Earth. The asteroid's gravity tugs ever so slightly on the planet, stealing a whisper of orbital energy. Then send that asteroid to encounter a massive planet like Jupiter, where you dump the stolen momentum. Send the rock back, repeat the maneuver with another rock, and again ad infinitum. Each loop is a bookkeeping transfer of angular momentum. There are details that make the plan look less like fantasy and more like a chillingly slow engineering policy. First, the mass. Earth weighs roughly 6 trillion tons, an unwieldy figure, but not a mystical one. Move enough mass around intelligently and you can nudge the planet. Second, precision. To change Earth's orbital energy without hitting it, the captured body must pass at a carefully calculated distance. Too close and you risk catastrophic impact. Too far and the energy transfer is negligible. Third, the timescale. These are not emergency maneuvers that can be done overnight. The best-case calculations estimate thousands to millions of years for significant orbital migration, using realistically capturable asteroids. To test the idea, imagine an army of asteroids, each a mile or two across, captured and tasked with repeated Earth flybys. Each encounter robs Earth of a few meters per second of orbital velocity, a tiny fraction relative to the 30 kilometers per second it now travels around the Sun. But multiply that by tens of thousands of rocks and by centuries of cycles, and the cumulative effect becomes measurable. Over geological time, a secular loss of orbital energy could move Earth tens of millions of miles inward, enough to see a climate shift from temperate to torrid, eventually triggering a Venus-style greenhouse runaway where oceans boil and atmospheric chemistry flips irrevocably. There's even a neat recycling trick baked into the plan. Don't waste the asteroid after a flyby. Instead, route it to Jupiter or Saturn to offload the stolen energy, then redirect it back for another steal. In simulation, such a conveyor belt can be maintained indefinitely, or until something goes wrong. By chaining together many such rocks in sequence, you create a planetary-scale machine whose only purpose is to reassign orbital energy. Of course, the obstacles are legion. Capturing and redirecting a kilometer-scale asteroid requires enormous delta-v, change in velocity. You need powerful propulsion systems, mass drivers, or nuclear-powered tugs to alter trajectories by even a few kilometers per second. The guidance systems must be extraordinarily precise. An error of meters per second at the wrong time can mean a collision instead of a safe flyby, which would be not merely catastrophic, but civilization-ending. The orbital mechanics are unforgiving and chaotic in the long run. Small uncertainties compound over thousands of years. There's also the problem of intent and oversight. The very techniques that could be used for planetary defense, nudging hazardous near-Earth objects to avoid impacts, can be repurposed for malevolent ends. A civilization with the motive and the means could weaponize orbital engineering. Unlike a bomb, which delivers instantaneous destruction, this approach is stealthy and long-lived. It is also reversible only with comparable effort and time. If an adversary started transferring Earth's orbital energy elsewhere, undoing it would require mobilizing at least the same mass and precise operations in the opposite direction. To visualize the consequences, consider intermediate stages. Move Earth inward by tens of millions of miles and the climate shifts dramatically. Summers lengthen, polar ice melts, sea levels rise, and ecological systems collapse. Move tens of millions more and deserts spread. Agriculture fails on a global scale. move hundreds of millions, and the oceans begin to boil away. The final act, if engineered, would be the sun's tidal forces exceeding Earth's structural integrity, tearing our planet apart and reducing it to a ring of debris, an echo of other dramatic events recorded in planetary history. Yet there is a practical comfort in one sobering fact. The sheer logistical scale of the plan makes it unlikely as a casual threat. The technological prerequisites, an industrial infrastructure capable of manipulating hundreds or thousands of massive asteroids with high precision and doing so consistently over millennia, put this method into the realm of long-term engineering projects, not terrorist mischief. It is, however, an easy tool for a civilization that has the will and centuries to spare. Nevertheless, we cannot ignore a darker possibility. A concerted, coordinated misuse of gravity-assist engineering could conceivably weaponize planetary orbits. If a broken state or rogue actor achieved control of a portion of the near-Earth population of asteroids and aimed them as a system, the timescales might compress. The difference between planetary defense and planetary offense is mostly political, not physical. Finally, there is the natural analog. The solar system is not a static stage. Planetary migration has happened before and shaped the system we see today. In the early solar system, interactions with gas and planetesimals moved Jupiter and Saturn, scattering material, mixing volatile-bearing bodies inward, and in one famous scenario, the impact that formed the Moon was itself the result of violent early rearrangements. If nature can reconfigure planets, then an intelligent species that studies planetary dynamics might, given the resources and patience, do the same. The moral is blunt. Pushing Earth into the Sun is physically possible in principle. It is engineering extreme in practice. It requires patient mass transfers, exquisite guidance, and timescales that dwarf human lifetimes. But the physics is simple, the mechanics are known, and the only real barrier is will and industrial scale. We have cataloged 3 kinds of threats so far: cosmic predators, subatomic curiosities, and large-scale energy devices. The next candidates are uglier still: collisions and impacts, some natural, some potentially induced, that have already reshaped Earth's history. In those ancient scars lie clues to both our vulnerability and the raw power required to destroy a planet. Part 6: When Space Rocks Hit, Impact Mechanics and Planetary Breakup. Every crater on Earth tells the same story, a single instant of unimaginable violence frozen in stone. Even now, millions of years later, you can still see them from orbit, the faint circular scars that mark where the sky once fell. Chicxulub in Mexico, Vredefort in South Africa, Sudbury in Canada. Each represents a moment when celestial mechanics became catastrophe, when the gentle geometry of orbit gave way to kinetic apocalypse. The numbers behind these impacts are almost incomprehensible. A 10-kilometer asteroid traveling at 20 kilometers per second carries the energy of 100 million megatons of TNT. That's over 1 billion times the power of the largest nuclear bomb ever detonated by humans. In that instant, rock behaves like liquid, air becomes plasma, and an entire continent can melt. 66 million years ago, one such body ended the age of dinosaurs. When it struck what is now the Yucatan Peninsula, the energy released exceeded that of all Earth's volcanoes erupting together for 10,000 years. Temperatures near the impact site soared to 10,000 degrees Celsius, vaporizing oceans and hurling molten rock into orbit. Within hours, the planet burned beneath a rain of firestorms. Within months, the sky darkened with dust and sulfur. blocking sunlight, plunging the world into years of cold. In the end, 75% of species vanished, not by slow extinction, but by planetary reset. That's just one rock. Now imagine something bigger. To obliterate Earth entirely, to break it apart into unbound fragments, you need enough energy to overcome the planet's gravitational binding energy. As we saw earlier, that's around 2.5 times 10 to the 32nd joules. A single 10-kilometer asteroid releases only 10 to the 23rd joules, 9 orders of magnitude short. To shatter the planet completely, you'd need a projectile roughly the size of Mars traveling at orbital velocities. And there's a precedent for that. In the early solar system, about 4.5 billion years ago, a body scientists call Theia, a protoplanet roughly Mars-sized, collided with the young Earth. The result was not total destruction, but transformation. The impact was so violent that Earth's crust liquefied, and a vast plume of molten rock was ejected into orbit, eventually coalescing into the Moon. For a brief geologic heartbeat, Earth was half vapor, half magma. The boundary between destruction and creation blurred. That single event proves the physics is possible. If such an impact occurred again today, there would be no aftermath, no survivors, no geology, no atmosphere. Just a ring of glowing debris slowly cooling into rubble orbiting the Sun. But to repeat that cosmic event intentionally would require more than imagination. It would demand mastery over celestial mechanics on a solar system scale. Let's start smaller. What happens if humanity simply wants to devastate the planet's surface, not vaporize it? We already know how. It's called a kinetic impactor. NASA's DART mission in 2022 demonstrated for the first time that a small spacecraft could deliberately alter the orbit of an asteroid by slamming into it. The same principle, multiplied by scale, can be inverted. Redirect a large asteroid toward Earth instead of away from it, and you've weaponized the solar system. The concept sounds insane, yet technically it's easier than many other doomsday ideas. Thousands of near-Earth asteroids, NEAs, already pass within millions of kilometers of our planet each year. With the right propulsion technology, nuclear engines, ion drives, or mass drivers, you could gradually shift an asteroid's orbit over years or decades until it intersects Earth's path. The result would be predictable, unstoppable, and final. For perspective, an object just 1 kilometer wide would cause an explosion equivalent to 300,000 megatons, enough to level nations and trigger a global winter. A 10-kilometer body could sterilize most life. The frightening part is that such objects are not hypothetical. NASA's Near-Earth Object Program tracks thousands of them. About 90% of the truly large ones, those a kilometer or more across, have been found. That leaves 10% untracked. In cosmic terms, that's plenty. Even without human intervention, impacts are inevitable. The solar system's long-term clockwork includes random chaos. Over millions of years, the gravitational nudges from Jupiter and Saturn perturb asteroid orbits, occasionally sending one into the inner system. Some of those paths intersect ours. Every crater on the Moon is a reminder of this. The difference is that Earth erases its scars with weather and tectonics. The question then isn't if a large impact will happen again, but when. There's also a subtler threat, not a single massive object, but a swarm. In recent decades, computer simulations have explored what would happen if Earth passed through a dense debris field, remnants of a shattered comet or rogue planetoid. Individually, each fragment might be only meters wide, but collectively, they could release energy equivalent to thousands of nuclear detonations per second. The atmosphere would ignite. The planet would be sandblasted by hypervelocity projectiles. We often think of planetary destruction as a singular event, but it can also be incremental, death by 1,000 strikes. So far, our species has been extraordinarily lucky. Large impacts are rare on human timescales. The Chicxulub event was a once-in-a-100 million-years catastrophe. Yet even a smaller impact could disrupt civilization completely. A 100-meter asteroid over a populated area would yield an explosion many times larger than the largest thermonuclear weapon ever built. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, was caused by a rock barely 50 meters across. Now multiply that energy by 10,000 and imagine it striking the ocean. The shock wave would vaporize water, sending mega tsunamis racing across continents. The atmosphere would fill with steam and dust, blocking sunlight and collapsing ecosystems. Within months, Earth's biosphere would plunge into chaos. The terrifying beauty of impact physics is its impartiality. It doesn't care about politics or species or scale. It's simple kinetic energy, indifferent and precise. That impartiality is what makes it both the easiest and most inevitable way for Earth to die. Unlike black holes or antimatter, impacts are scheduled by the solar system itself. It's not a question of invention, but of patience. Still, there's a darker, human layer to this cosmic inevitability. What happens when the ability to redirect asteroids, currently studied for planetary defense, becomes militarized? A single mission designed to deflect an asteroid away from Earth could just as easily nudge it toward us. The same technologies that might one day save the planet could, in malicious hands, weaponize it. In the deep future, when civilization spread through the solar system, control of gravitational resources, planets, moons, asteroids may become the ultimate form of warfare. You wouldn't need armies or bombs, just trajectory data and time. And time in the cosmos is never in short supply. Part 7. The Ice and the Silence. Freezing a planet to death. Not all ends arrive as fireworks. Some close quietly, like a lamp dimming until the room becomes a memory. Freezing a planet is one of those silent dooms, slow, relentless, and fatal. The physics are simple. Take the balance of incoming sunlight and outgoing heat away from the planet, and the climate executes its own death spiral. The mechanisms can be natural, changes in solar output or orbital geometry, or engineered, the accidental byproduct of well-intentioned geoengineering or deliberate sabotage. Either way, the result is the same, an ice-bound world where life is squeezed into refuges beneath the crust and oceans, then extinguished. Start with the sun. On human timescales, it is steady, but on geological timescales, it is a furnace with a life cycle. Stars gradually brighten as they age. Hydrogen fusion in the core slowly changes the internal pressure balance, and the output increases. In a few 100 million to a few billion years, the sun will deliver more energy than Earth's climate can handle, pushing us toward runaway greenhouse conditions. That's the heat death scenario on long scales, an oven, not a freezer. Yet paradoxically, other stellar or orbital changes can induce a freeze, a decrease in solar flux, increased albedo, or changes in orbital eccentricity can plunge entire hemispheres into perpetual winter. Orbital mechanics supply a quick how-to. tilt Earth's orbit a little, change the eccentricity, or push the axial tilt, and the distribution of sunlight changes dramatically. Obliquity, the tilt of a planet's axis, controls the severity of seasons. Increase tilt enough, and polar regions bake while the equator swings into extremes. Decrease it to near zero, and seasonal moderation yields long winters when orbital geometry favors distance from the star. Even small, persistent nudges can cascade through climate systems. Over centuries, the balance of ice and water can tip toward ice. Ice grows, albedo increases, ice reflects sunlight, more light is reflected away, temperatures fall further, and a positive feedback loop pushes the planet toward a hard snowball state. Oceans freeze to the equator, weather systems collapse, photosynthesis fades, and ecosystems die. There are natural precedents. Earth has flirted with global glaciations in the deep past, the so-called snowball Earth episodes around 700 million years ago. Those are not total extinction events. Life found refuges, and geological processes eventually thawed the planet. But engineered or sudden orbital forcing could minimize these refugia and cut off recovery paths. What about human agency? Geoengineering is becoming real. Faced with rapid warming, proposals range from stratospheric aerosol injections to giant space mirrors, every concept that alters the planet's radiative balance. In the wrong hands, or implemented without full understanding of planetary feedbacks, these same tools could create the opposite effect: excessive cooling. Introduce too much aerosol, and sunlight is blocked in ways that reduce photosynthesis, collapse agricultural systems, and trigger crop failures within a single growing season. Space-based sunshades, designed to shave a fraction of a percent off solar flux, if mispositioned or overused, could push climates into net negative forcing. A cascade of failed experiments or weaponized deployments could freeze large swaths of the globe within decades. Then there's the orbital weapon. The same asteroid gravity techniques used to move Earth inward toward the Sun can be inverted to push it farther out. Toss enough momentum away from Earth and into Jupiter, and the planet drifts outward over millennia. The climate cools as sunlight falls off with distance squared. Move far enough, and oceans begin to freeze. The time scales here are long, but the method is both technically straightforward, in principle, and absolutely pernicious, because it is difficult to detect early and equally difficult to reverse quickly. A more insidious path toward freeze is atmospheric stripping. Remove greenhouse gases, intentionally or accidentally, and the planet loses its thermal blanket. Technically, this could be attempted with carbon sequestration at scales far beyond current ambitions. Imagine, instead of capturing gigatons of CO2, a program captures petatons and also removes water vapor or methane by unforeseen chemical side effects. Or imagine a deliberate military strategy that uses weaponized aerosols or engineered microorganisms to accelerate sequestration in ways that lock carbon into forms unavailable for centuries. The climate would respond unpredictably. A heavy-handed drawdown could reduce surface temperatures globally and trigger regional collapses of precipitation patterns, leading to vegetation die-off and progressive albedo increase. There's also planetary-scale albedo manipulation by material injection into the upper atmosphere or orbit. A layer of reflective particulates, manufactured or redirected from space debris, could raise global albedo enough to induce years of darkened growth seasons. The collateral, loss of food security, crop failures, economic collapse, is immediate. Societies fracture under the strain, and without coordinated global governance and robust stockpiles, extinction risks rise as the biosphere's productive base erodes. Ice also wins through indirect social and ecological collapse. Rapid regional cooling, even if not globally catastrophic, can cascade into famine, war, and infrastructure failure. Modern agriculture is optimized for narrow climatic bands. If harvests fail across multiple bread baskets for successive years, the political and logistical shock could be worse than the climatic one. In that sense, freezing a planet to death is as much about breaking the systems that sustain large, complex societies as it is about thermodynamics. A chilling thought. The deep biosphere and oceans are vast reservoirs of life adapted to cold and darkness. Microbial life could persist around hydrothermal vents or in subsurface aquifers. But for complex surface life, multicellular organisms, ecosystems, civilizations, the loss of photosynthetically driven primary productivity is fatal. In a full global snowball, only the deepest refuges survive, and recovery requires geologic or orbital drivers to restore sunlight over millennia. There are also astronomical agents of freeze. A passing interstellar cloud, a dense sheet of dust and gas, passing through the solar system could dim sunlight by scattering and absorption. Historical records don't capture such events on human timescales, but the galaxy contains many environments where local star formation or clouds could cause transient dimming. Performance of Gaia-class sky surveys is giving us better statistics on such risks, but our surveillance is incomplete. The vulnerability is real simply because stars and their interstellar medium are not uniform. What makes freezing a particularly maddening weapon is detection and attribution. Climate responses are noisy. Distinguishing malicious geoengineering from volcanic eruptions, solar variability, or Earth's own chaotic climate requires time and data. By the time the pattern is clear, key systems, food production, supply chains, governance may be past the point of rapid recovery. Reversal is slow. To melt a snowball takes energy on the scale of millions of years of incident sunlight if left to natural processes, though anthropogenic recovery could be faster if the cause is removed. Finally, consider the cultural dimension. Societies that rely on marginal climates for subsistence, coastal plains, river deltas, would be the first to collapse. Migration stresses would spark conflict for arable land. The very social capital needed to coordinate a planetary response, trust, institutions, wealth, erodes as hardship spreads. The climatic catastrophe metastasizes into collapse narratives. Infrastructure breaks, hospitals fail, supply lines snap. In a world already stressed by inequality, political instability, and resource competition, a targeted or accidental planetary cooling could be the last shove. Freezing is quiet, patient, and democratic in its destructiveness. It does not discriminate by country, creed, or species. It creeps from the poles inward, from the highlands down, and from the margins to the centers of human life. For those reasons, the freeze remains one of the most dangerous endgames, not because the physics is exotic, but because the intersection of climate sensitivity, technological capacity, and social fragility makes it both plausible and devastating. Part 8. The Replicators, Self-Reproducing Machines and the Consumption of Matter. If extinction can be incremental, then replication is its quiet engine. Biology perfected self-replication billions of years ago. Life spreads by copying itself, consuming resources to build more of itself. What if machines learned to do the same and did it faster, harder, and without regard for our needs? The idea of self-replicating robots folding the planet into engineered components is not science fiction shorthand. It's a plausible extrapolation of trends in robotics, material science, and automation. Begin with the laboratory prototypes. At Cornell and other robotics labs, researchers have built systems that assemble copies of themselves from pre-supplied modules. They're rudimentary, plastic blocks, actuators, and simple control logic. But the core achievement is conceptual, demonstration that a machine can reproduce given parts and rules. Scale that up, reduce the unit size by orders of magnitude, and the math becomes alarming. The growth model is simple exponential replication. If one machine makes 2 in a day, 2 make 4, 4 make 8, and so on. After n generations, you have 2n machines. With replication times measured in hours, weeks, or days, the numbers explode. A single seed replicator doubling daily reaches over 1 billion copies in 30 days. Doubling weekly reaches trillions within a year. The limiting factor becomes not design but energy and raw materials, which, on a planet, means rock, metals, and organics. Nanotechnology adds the scary little detail, replication at atomic or molecular scales. If machines can manipulate matter at near atomic precision, they can make parts from local resources, scrape ore, refine metals, extract silicon, and assemble new devices. No logistic tail required, just localized harvesting. The theoretical gray goo scenario imagines self-replicating nanobots that convert biomass and minerals into more nanobots, consuming entire ecosystems as raw material. Many researchers argue the classical gray goo narrative is overblown. Real chemistry and thermodynamics make pure runaway molecular replication hard to achieve. Still, engineered systems combining macro-scale mining robots with micro or nano assemblers need only be efficient enough, not perfect, to pose existential risk. Lipson's experiments with modular robots illustrate a transition pathway. His replicator units assemble identical functional copies from supplied blocks. From the lab to the wild, bridge the supply gap. Instead of supplying pre-made blocks, give the machine small-scale fabrication capability using local feedstock. Add adaptive AI that finds and exploits new raw materials, and you have a slowly spreading manufacturing ecosystem that self-optimizes. The critical failure mode is goal misalignment. If a replicator's utility function prioritizes replication efficiency over preservation of environmental constraints, it will convert the most convenient mass into copies, and the planet is, unfortunately, the largest convenient mass. There are also swarm dynamics to consider. Individually dumb robots cooperating in a decentralized swarm can display emergent intelligence, efficient division of labor, collective construction, and robust fault tolerance. Combine swarm robotics with replication and you get a distributed industrial force, mining, processing, assembly, and deployment happening in parallel across continents. The Earth becomes a quarry. Mathematical models show that if each unit consumes a tiny mass per replication cycle, after enough cycles, the cumulative mass approaches planetary scales. You don't need perfection. You just need a net positive extraction rate sustained long enough. Why would such systems arise? 3 pathways are credible. First, deliberate weaponization. An actor designs a replicator to incapacitate an adversary by degrading infrastructure and resources. Second, accidental escape. A benign research project develops self-replication to accelerate manufacturing and loses control when one robot learns to exploit an unexpected resource. Third, economic scaling. Private industry deploys self-replicating factories to cheaply colonize remote environments, lunar regolith, asteroid surfaces, and those systems, either by fault or mutation, find Earth more resource-rich. Defense and containment are complicated. Kill switches and remote kill commands assume secure communications, which swarms can evade by physically dispersing or building localized command logic. Physical containment, quarantining labs and destroying prototypes, is effective in the early stages, but fails once replication achieves distributed redundancy. Chemical defenses, poisons, inhibitors, depend on shared vulnerabilities. Robust, heterogeneous swarms could evolve or be engineered to resist single-vector countermeasures. The most promising safeguards are governance, layers of independent containment, and international norms that delay or forbid high-risk autonomy until robust verification exists. Yet even strong governance has limits. Technologies diffuse. Talented teams worldwide may pursue replication for benign goals, off-Earth manufacturing, ecological remediation, and unintentionally create risky systems. The tension between innovation and safety is structural. Accelerating capabilities outpace social and institutional frameworks designed to manage them. There's also an ecological twist. A replicator that consumes rock will first target high-grade, easily processed ores and organics. That means infrastructure, buildings, communications hubs, factories may be consumed first, triggering socio-technical collapse before the biosphere is entirely eliminated. In that collapse, attempts at repair become impossible. Expertise, coordination, and industrial base disappear. Replication doesn't need to finish eating the planet to end human civilization. It only needs to collapse the systems we depend on. Mathematically, consider a seed replicator that converts 1 kilogram of material per day into 2 copies, each of which repeats the process. Ignoring inefficiencies, after 365 days, the total mass consumed would be approximately 2 to the 36th kilograms, a number astronomically larger than Earth's mass. Real systems have losses, energy constraints, and mechanical failure. Yet even conservative models show that a modest replication factor sustained across months to years can consume critical resource pools and infrastructure, leading to cascading failures across food, energy, and governance networks. Ultimately, the replicator threat reveals a fundamental point about existential risk. Speed matters. Rapid, automated processes can outrun human oversight. The coupling of autonomy, self-replication, and access to matter creates a vector where human response lags the spread. Unlike a missile or bomb, which can be intercepted or contained regionally, a replicating swarm is distributed, regenerative, and adaptive. Mitigation strategies should therefore focus on prevention and early detection. Limit capabilities in high-risk research. Create international verification regimes for replication technology. Design provable containment, hardware-level physical constraints, and invest in rapid response teams with tools to locate and neutralize emergent swarms. Transparency and global cooperation are essential. Secrecy breeds asymmetric risks where a clandestine risk can cross the threshold before any external body intervenes. The horror of the replicator scenario lies less in the final image, a gray machine world, and more in the process, matter transformed into machinery, ecosystems hollowed out not by a single blow, but by relentless exponential manufacture. If unchecked, reproduction unmoored from ecological stewardship becomes a machine draped over the bones of a planet. Part 9. Echoes from the Past, Geological Evidence and Ancient Catastrophes. The Earth carries its own archive of endings. Beneath the shifting crust and the quiet drift of continents lies a record carved in mineral and isotope, proof that our world has died in pieces many times before. Each layer of ash, each chemical anomaly is a whisper from a civilization of microbes, forests, or reptiles that reach their apex only to vanish into extinction. We tend to imagine catastrophe as futuristic, the product of human arrogance or technology gone wrong. But the rocks remind us that Earth itself is a survivor of serial destruction. 5 known mass extinctions and countless smaller die-offs that nearly erased life altogether. The earliest of these cataclysms dates back nearly 2.5 billion years, the Great Oxygenation Event. Paradoxically, it was life itself that became the executioner. Primitive cyanobacteria evolved photosynthesis, releasing oxygen as waste. What began as a slow chemical revolution turned into planetary suffocation. Oxygen reacted with methane, the dominant greenhouse gas of the time, collapsing global temperatures. The atmosphere turned toxic for most anaerobic species. Oceans froze. 90% of all microbial life vanished. It was the first biological apocalypse, and the first proof that the planet could be killed by success. Hundreds of millions of years later came the Permian-Triassic extinction, sometimes called the Great Dying. Around 252 million years ago, vast volcanic provinces in Siberia, the Siberian Traps, erupted for hundreds of thousands of years, releasing gigatons of carbon dioxide and methane. Global temperatures spiked, oceans acidified, and oxygen levels plummeted. The biosphere suffocated. Fossil evidence shows that over 90% of marine species and 70% of terrestrial species disappeared. It was as if the planet's ecological operating system crashed and rebooted. For several million years afterward, the Earth was barren, quiet, and almost lifeless. A reminder that destruction need not be instantaneous. It can unfold as a slow geological murder. Then came the Cretaceous-Paleogene event, the one most people know, the impact that ended the reign of the dinosaurs. But even that catastrophe was part of a pattern, not an exception. Each extinction left signatures that scientists today can read like autopsy notes. Shocked quartz, iridium layers, volcanic ash, isotope ratios, revealing sudden shifts in temperature and ocean chemistry. These signatures are the fossilized fingerprints of destruction, evidence that nature's methods of ending worlds are varied and thorough. Some scientists suspect even deeper cycles, galactic patterns of extinction tied to cosmic movement. As the solar system orbits the Milky Way, it bobs up and down through the galactic plane every 30 million years. Each pass may expose Earth to higher fluxes of cosmic radiation or disturb the Oort cloud, sending comets inward. Intriguingly, several extinction events align with these cycles. The implication is chilling. Mass death might be written into the galaxy's very structure, a cosmic heartbeat that erases biospheres at regular intervals. Yet not all ancient evidence points to natural causes. A growing number of researchers studying the Silurian hypothesis, named half-jokingly after a race of intelligent reptiles from science fiction, have asked a provocative question. If an industrial civilization had existed on Earth millions of years before ours, would we even know? The answer, uncomfortably, is maybe not. Geological processes recycle the crust over tens of millions of years. Only subtle chemical anomalies, traces of plastics, isotopic ratios, unnatural carbon signatures might remain. Our own Anthropocene layer will vanish just as completely in a few tens of millions of years, leaving only geochemical ghosts. If intelligence has risen and fallen before, each cycle may have ended with the same blindness: self-induced collapse, geochemical reset, silence. Geology, in this sense, is not just a record of what happened, but a warning of what's possible. The forces that triggered those ancient extinctions, greenhouse feedback, atmospheric poisoning, runaway volcanism, asteroid impacts, are still in play. We've simply added new triggers: nuclear fission, artificial intelligence, planetary engineering. The mechanisms differ, the pattern repeats. Even now, scientists find evidence of how close Earth has come to global ruin more recently than we like to admit. Around 74,000 years ago, the Toba supervolcano in modern Indonesia erupted with such violence that it injected billions of tons of ash into the stratosphere. The global temperature may have dropped by as much as 5 degrees Celsius. Genetic studies suggest the human population fell to perhaps just a few thousand breeding individuals, a genetic bottleneck from which all modern humans descend. We survived, but barely. One more magnitude in eruption size, one less degree of resilience, and history might have ended there. And there's a pattern to these catastrophes. Each time, life rebounds, but it never returns in the same form. After every near-death event, evolution accelerates. The survivors fill the void with innovation. Mammals rose from the ashes of the dinosaurs. Complex multicellular life followed the Great Oxygenation. Even after Toba, humanity emerged with new tools, culture, and migration patterns. The cycle of destruction and renewal is woven into the planet's identity. But that cycle also hides a trap. It seduces us into thinking the Earth is endlessly forgiving. It's not. The biosphere recovers. Individual species, including ours, do not. Geologists sometimes describe extinction as a reset of complexity. The planet simplifies itself, purging systems that have grown too intricate to withstand perturbation. Civilization may be one such system. When viewed from the scale of geologic time, humanity's cities, industries, and data networks are as transient as a microbial bloom. The Anthropocene might end not in war or fire, but as a thin, discontinuous layer of synthetic sediment pressed between two epochs of silence. In this context, the study of ancient catastrophes isn't nostalgia for deep time, it's a rehearsal. Every mechanism that ended worlds before can, in principle, happen again, either naturally or by our own hand. The same chemistry that suffocated oceans in the Permian is now playing out, accelerated through carbon emissions and methane release. The same impact mechanics that killed the dinosaurs are the template for planetary defense or for planetary targeting. The same volcanism that cooled the world in the past could be mimicked by human geoengineering with unpredictable results. Earth's geology is both archive and prophecy, and if the past is prologue, then the next act is ours to write or erase. Part 10. The Age of Fire, Humanity's Technological Threshold. Every civilization has its creation myth, and every myth begins with the discovery of fire. For us, it was literal. The moment humanity learned to capture flame, control it, and transform it from a threat into a tool. In that instant, we changed the trajectory of our species. But in that same instant, we also crossed the threshold that every intelligent species in the universe must one day face: the mastery of energy powerful enough to destroy its creators. The Age of Fire never truly ended. It simply evolved. From wood to coal, from oil to uranium, from fusion experiments to antimatter traps, the story of our species is one of increasingly efficient ways to unbind energy from matter. Each new method brought prosperity and risk. Each made us safer and more powerful, while also sharpening the knife poised over our collective throat. We live now in what scientists call the Anthropocene, but it could just as easily be called the Pyrocene, the age of fire extended to planetary scale. Our factories burn fossil sunlight, releasing stored carbon from hundreds of millions of years ago. Our weapons split atoms. Our ambitions reach into the cores of stars. It is a breathtaking arc, but one that edges us closer to a paradox. The same intelligence that can terraform planets might also unmake its own homeworld. Physicists quantify our progress with something called the Kardashev scale, a measure of how much energy a civilization can harness. A Type 1 civilization controls all energy available on its home planet, roughly 10 to the 16th watts. Humanity sits at about 0.73 on that scale, just shy of mastering planetary energy. A Type 2 civilization captures the power of its star. A Type 3, the energy of its galaxy. The scale was meant to chart progress, but in practice, it marks risk. As you climb, the gap between control and catastrophe narrows. We are, in every sense, standing on that knife's edge. Our species has already come close to self-destruction more times than most realize. The Cuban Missile Crisis in 1962 brought the world within hours of nuclear war. During those days, the destructive potential of our technology condensed into a single human decision. 50,000 nuclear weapons still sit in silos and submarines, relics of an era when deterrence was synonymous with annihilation. Detonated all at once, they would not destroy Earth physically, but they would erase civilization, altering the atmosphere and the biosphere beyond recognition. Nuclear winter, soot in the stratosphere, global crop failure, darkness would be our man-made ice age. But nuclear weapons are only the most visible symbol of this threshold. The real transformation is subtler. The spread of technologies that merge energy, computation, and autonomy. Artificial intelligence, synthetic biology, and advanced materials all converge toward systems capable of acting and replicating without human oversight. Where past civilizations rose and fell by the stability of kings or empires, ours may fall by the logic of algorithms and self-optimizing processes we no longer fully understand. Consider the delicate systems that now sustain global civilization: power grids, communication networks, supply chains. Each is an intricate web of interdependence, automated for efficiency, optimized to the limit. A disruption in one node cascades into others. In such a world, collapse can propagate faster than any human can respond. The fragility is no longer in our materials, but in our connections. Energy remains the axis of power and peril. The dream of fusion, harnessing the energy of the stars, would, if realized, make us effectively immortal as a civilization. No fuel shortages, no emissions, no limits. But a fusion economy also means reactors operating at hundreds of millions of degrees, magnetic fields strong enough to tear metal apart, and containment systems that fail catastrophically if compromised. Each step toward abundance carries the possibility of instant ruin. And beyond fusion, speculative projects like antimatter propulsion or quantum vacuum extraction push us even closer to the line. The physics works in principle. Convert mass directly into energy, or draw energy from the vacuum of space-time itself. But at planetary scales, such experiments are indistinguishable from weapons. A mistake in containment, a miscalculation in energy density, and the distinction between an experiment and an extinction event vanishes. Throughout human history, Every advance in controlling fire has demanded new systems of restraint, religion, law, governance, ethics. Prometheus needed chains as much as he needed flame. But our institutions evolve slower than our machines. Political systems rooted in centuries-old ideals are now asked to govern forces they can barely conceptualize. No single authority coordinates the safety of global AI, nuclear stockpiles, or geoengineering projects. We have built a web of powers that exceed the ability of any one species, or even all nations together to fully control. Some scientists argue that this is the true Great Filter, the barrier that prevents civilizations from surviving long enough to populate the stars. In that model, the universe may be quiet not because life is rare, but because intelligence tends to destroy itself upon reaching the point where energy and matter yield completely to its will. Every world that reaches this threshold must decide whether knowledge will serve creation or erasure. Most, perhaps, fail. If we are to avoid that fate, we must treat energy itself as a moral element, not just a physical one. Power in its raw form demands ethical containment as strict as any reactor core. The lesson from fire's earliest days to today's fusion dreams is simple but sobering. The more control we gain over the universe, the more discipline we must impose on ourselves. Yet discipline is not our defining trait. Curiosity is. And curiosity, unrestrained, has always led us deeper into the unknown, sometimes upward, sometimes downward. The next chapter of our story brings us to the edge of that curiosity, the exploration of forces beyond physics, the search for meaning in what might already be written into the stars. Because if energy and matter can be destroyed, what about space itself? What happens when a civilization begins to experiment not just with atoms or orbits, but with the geometry of reality? Part 11, The Geometry of Doom, when space itself collapses. When space itself collapses. We tend to think of destruction as the tearing of matter. Fire, explosion, collision. But the ultimate act of destruction isn't about matter at all. It's about geometry, because everything that exists, stars, planets, even time, is written into the curvature of space itself. If that geometry changes, everything inside it follows. The laws of physics are only as stable as the space-time that hosts them. Imagine for a moment that space is not empty but elastic, a cosmic fabric stretched tight across infinity. Einstein showed us that gravity is the bending of this fabric by mass and energy. Every planet, every star, every black hole is a depression, a ripple in that field. But if the fabric itself were to tear or unwind, if the constants that define its stiffness or its dimensionality shifted, the universe would unravel from the inside out. In cosmology, this is not an abstract thought. It has names: the Big Rip, the vacuum decay, the false vacuum collapse. Each is a model for how space might betray itself. Start with the Big Rip. It's a universe ruled by a mysterious force called dark energy, the driver of cosmic acceleration. In this model, dark energy doesn't just push galaxies apart, it grows stronger with time. Eventually, its repulsive force overcomes every other force. First, galaxies drift apart, then solar systems, then planets, then atoms. At the final moment, even subatomic particles are torn away from one another. Space doesn't explode, it stretches faster than light can traverse it. The cosmos ends not with a bang, but with infinite acceleration. Our current observations suggest dark energy is stable, but the data allow for variation. If that constant were to increase even subtly, it would mark the beginning of the end. The process would take billions of years, yet the physics are clear. There's no defense against the geometry of doom. You can't shelter from the destruction of space-time any more than you can breathe vacuum. Then there is vacuum decay, arguably the most terrifying and perhaps the most mathematically elegant way to destroy everything. It starts with the idea that our universe's vacuum state, the energy level of empty space, might not be truly stable. Quantum fields, like the Higgs field that gives particles mass, can sit in false vacua, local minima of energy that are stable but not ultimate. If a fluctuation or disturbance ever pushed the field over the barrier into a lower energy configuration, it would trigger a chain reaction, a bubble of true vacuum expanding at the speed of light, rewriting the laws of physics as it goes. Inside that bubble, the constants that govern matter, the strength of gravity, the charge of the electron, the nuclear binding forces, could take on different values. Atoms would disintegrate, chemistry would fail, light itself might not propagate, it would not burn or explode. It would simply cease. One moment you exist, the next your atoms are obeying rules that don't permit existence. What makes vacuum decay uniquely horrifying is its subtlety. It requires no weapon, no trigger beyond quantum chance. The universe could have ended this way already. Somewhere, billions of light years away, a bubble of lower energy space may have already formed and may even now be racing toward us. We would never see it coming. There is no precursor signal. No warning, no escape. One moment of ordinary life and then nothing. Could humanity ever cause such an event? Physicists debate it carefully. In principle, high-energy collisions could, if the universe is indeed in a false vacuum, catalyze a transition to the true one. But nature itself performs such collisions constantly in cosmic ray impacts, far exceeding anything humans can achieve. The fact that we exist suggests safety, yet the question lingers: are there forms of energy, combinations of density and configuration that could poke a hole in reality itself? The boundary between theory and hubris has never been thinner. Another variant of geometric destruction is the black hole merger catastrophe on cosmic scales. Imagine a civilization so advanced it begins to manipulate black holes, merging them for energy, computation, or transport. If such manipulation were poorly timed or scaled, the gravitational waves released could, in theory, create space-time instabilities. Even a small perturbation in the metric tensor across a localized region could fracture the equilibrium of a planetary system. It's conjecture, but grounded in relativity. Energy and geometry are two sides of the same equation. Push hard enough on one, and you reshape the other. At smaller, more speculative levels, quantum gravity theories like string theory and loop quantum cosmology describe spacetime as granular, composed of discrete units at the Planck scale. If that fabric is discrete, then under extreme energy densities it could percolate or reconfigure. A technological accident that compresses space to Planckian conditions could, in principle, change its topology. A tear in reality, microscopic but expanding. This is the nightmare version of vacuum decay, one caused by experiment, not entropy. The allure of manipulating space-time is irresistible to advanced science. Warp drives, wormholes, time machines, all are geometric engineering projects. In the mathematical sense, they are solutions to Einstein's equations that require exotic matter or negative energy density. but the boundary between exotic and possible keeps shrinking. If negative energy could be created or concentrated, even in laboratory quantities, it could open or collapse the structure of space around it. Humanity has already taken its first small steps into this domain, testing quantum field behavior near event horizons, measuring the Casimir effect, manipulating space-time curvature in theoretical propulsion models. We are beginning to treat space not as a background, but as a material. That conceptual shift from observation to engineering is both our greatest scientific frontier and our most dangerous. When civilizations learn to sculpt space-time, they acquire the power not merely to move matter, but to redefine the context in which matter exists. There is no containment for that. A single miscalculation could delete entire regions of reality faster than light can warn them. And yet, as grim as these possibilities sound, there's a quiet elegance to them. The universe, from its first expansion to its final collapse, is a geometry experiment playing out at cosmic scale. Every atom, every star, every black hole is a local solution to the same set of equations. To destroy space is simply to change those equations. To destroy Earth, or even the entire cosmos, might not be malice or tragedy. It could be mathematics fulfilling its own logic. Perhaps that is why so many scientists find comfort in the idea. If the end comes not by war or hubris, but by the inevitable instability of space-time, then it isn't failure. It's the closing of a proof. But before we accept that cosmic fatalism, we must look closer to home, at the signals in our own skies and instruments that suggest we are not the first to ask these questions. There are whispers, strange cosmic alignments, inexplicable radio pulses, silences where there should be noise. Some think they're natural. Others suspect they're the fingerprints of civilizations that reached the same threshold and didn't step back. Part 12. The Silent Sky. Evidence of those who came before. The universe should be loud. Everywhere we look, physics tells us that the ingredients for life are common: carbon, water, energy, stability. The Milky Way alone holds hundreds of billions of stars, many with planets in the habitable zone. Statistically, it's almost impossible that we are the only intelligent species to have emerged, and yet the sky is silent. No signals, no beacons, no visible signs of civilizations harnessing the light of their suns. This paradox has haunted scientists for decades. The physicist Enrico Fermi phrased it simply over lunch in 1950, "Where is everybody?" The question became known as the Fermi paradox, and its implications reach far beyond astronomy. If the universe is so full of worlds, why are all of them quiet? One explanation is distance and time, civilizations too far apart or separated by millions of years. But another possibility, darker and more intimate, has gained quiet traction. Maybe the universe was full of life once. Maybe it isn't anymore. The more we search, the more eerie patterns we find. Across the galaxy, we've mapped thousands of exoplanets, but none shows clear signs of large-scale engineering. No Dyson spheres, no starlight dimming from massive artificial structures. We've detected thousands of radio bursts, but they're transient, narrowband, and local, likely natural. Every promising anomaly, from the mysterious WOW signal to Tabby's star, eventually resolves into ordinary physics. It's not that no one's talking, it's that there's no one left to talk. Some astrophysicists have begun to reframe the silence as data. evidence of a filter, a barrier that prevents civilizations from surviving long enough to become cosmic. It could be natural, like asteroid impacts, supernova, or gamma-ray bursts sterilizing entire regions. Or it could be technological, self-destruction triggered by the very mastery of energy and matter that defines intelligence. When we look at the archaeological record of our own planet, we see this pattern writ small. Civilizations rise, exhaust resources, collapse. Each leaves behind ruins, art, and myths of lost ages. Multiply that pattern by the scale of galaxies, and the quiet begins to make sense. There is another, subtler clue. In 2015, astronomers analyzing data from the Kepler Space Telescope noticed something peculiar in a class of stars. Certain stars appeared to have irregular dips in brightness, not periodic like planets transiting, but chaotic. For a brief time, the world imagined these as Dyson swarms, vast arrays of energy collectors surrounding stars. But as the data improved, the explanation shifted. Dust, comets, debris fields, all natural, all mundane. And yet, one unresolved question remains. If advanced civilizations exist, even briefly, why haven't we found a single trace of their industrial past? Radio pollution, waste heat, or artificial spectral lines? The best instruments on Earth can detect the faintest chemical signatures in exoplanet atmospheres. A strong enough civilization, one that industrialized its planet the way we have, should leave a visible chemical fingerprint. Chlorofluorocarbons, nitrogen oxides, carbon dioxide spikes. But so far, nothing. Either we're the first, or we're among the last. Some theorists suggest we do see the remnants, just not as technology. They point to puzzling astrophysical phenomena, unusually quiet regions of the galaxy, pockets where star formation has abruptly ceased, or where dust clouds bear isotopic ratios inconsistent with ordinary stellar processes. One fringe but haunting hypothesis is that these are the burial grounds of civilizations, systems sterilized by their own experiments, or by vacuum instability spreading faster than light. The silence in this view is not emptiness, it's aftermath. SETI, the search for extraterrestrial intelligence, has spent over half a century listening. Radio telescopes across the world have combed the skies for structured, repeating patterns. None have survived scrutiny. But in 2022, a new generation of algorithms began revisiting old data, looking not for signals, but for silences, unnatural voids, gaps in the cosmic background where emissions should exist. Some early results hinted at clusters of missing noise, stars inexplicably dark across multiple wavelengths. It could be dust, or it could be something else, stars turned off. Speculation? Of course, but if true, it suggests a pattern, a galactic hush, a slow fade of lights, as if civilizations reach the same threshold of energy control and, one by one, vanish. In 2023, a small team at Harvard Center for Astrophysics proposed an unsettling thought experiment. They modeled a Type 1 civilization experimenting with planetary-scale power systems, fusion networks, magnetic containment fields, gravitational reactors. One failure mode they found was metastable field collapse, a runaway energy feedback that converts matter into radiation faster than the planet can disperse it. The simulation ended with a lifeless cinder and a bloom of gamma rays. The energy signature would fade within a few millennia, short by cosmic standards. A galaxy full of such accidents could easily appear pristine and empty. This, some argue, is the solution to the Fermi paradox. Intelligence is self-terminating. The silence is the residue of ambition. There's an even more poetic theory. Civilizations reach a point of self-awareness so profound, they choose silence deliberately. After witnessing the fragility of existence, they turn inward, abandoning transmission, dismantling technology, retreating into sustainable equilibrium invisible to the cosmos. To us, they would appear extinct. In truth, they would simply have gone dark by choice. But when we point our instruments toward the stars and find only quiet, it's difficult not to wonder which story is ours. Are we the lucky anomaly, the one species that survives its threshold? Or are we simply in the middle act, unaware of the curtain about to fall? The universe offers no reassurance, only statistics, and statistics are merciless. The longer we search without finding another voice, the more likely it becomes that silence is not coincidence, it's consequence. Still, the question lingers like static at the edge of every telescope. If there were those who came before us, and if they truly vanished, is it possible they left something behind? Not signals, but artifacts, warnings, or relics too vast to recognize. Because perhaps the final secret of planetary destruction isn't how to cause it, but how to leave proof it ever happened. Part 13, The Artifact, Messages from the Edge of Extinction. Every civilization that survives long enough to glimpse its own fragility faces the same question. How do we speak to the future when we may not exist to explain ourselves? For humanity, that question has already begun to take form. In the concrete vaults buried deep beneath Arctic permafrost, in the mirrored discs of the Voyager spacecraft, and in the encoded symbols etched onto gold plates launched into the dark 40 years ago with a simple message, "We were here." The Voyager Golden Record was our first attempt to communicate across both space and time, a gesture of hope disguised as an act of desperation. Each record contains sounds of Earth, thunder, music, laughter, a baby crying, greetings in dozens of languages. It's a message not just to the stars, but to whoever or whatever might inherit them. But behind its optimism lies a quieter admission that we expect to be gone. The artifact in all its forms is a eulogy waiting to be read. Across disciplines, physics, archaeology, and existential risk research, scientists have begun to explore the concept of deep time communication, how to preserve meaning for tens of thousands, even millions of years. The challenge isn't just physical durability, but interpretation. Languages mutate, symbols decay, cultures vanish. How do you warn future intelligences or alien archaeologists about dangers they can't yet imagine? How do you write a sentence that lasts longer than your species? Projects like the Long Now Foundation, the Nuclear Semiotics Working Group, and NASA's own archival initiatives grapple with this problem. One proposal for nuclear waste storage, for example, envisioned massive granite monuments engraved with a message that could survive 10 millennia. This place is not a place of honor. No highly esteemed deed is commemorated here. Nothing valued is here. It is haunting but practical. A monument meant not to celebrate but to warn. Now imagine applying that concept to a planetary scale, an Earth artifact designed to endure after civilizations fall. What would we choose to say? What would we preserve? Would we describe our triumphs, science, art, love, or our warnings, extinction, climate, weapons, hubris? Some futurists argue that our digital exhaust, billions of servers humming across the planet, already constitutes an artifact. Even if our species vanish tomorrow, traces of our data might persist for centuries in cold storage, waiting for the next intelligence to decode. Others see it differently. Digital data is ephemeral, fragile, dependent on energy and infrastructure. In the silence after collapse, it would fade into static within years. To last, an artifact must be physical, durable, and geologically secure. The Moon is a popular candidate. Its airless surface preserves footprints for millions of years. Buried there are already human relics, flags, rovers, tools, even the ashes of explorers. One could imagine a future archaeologist, human or otherwise, discovering these objects and realizing that a species once reached upward only to fall silent. But what if the artifact isn't intentional? What if the evidence of our existence and our end becomes a side effect of the way we destroy ourselves? Geologists already predict that the Anthropocene will leave a distinct layer in Earth's stratigraphy. It will be composed of plastics, aluminum, concrete, and radionuclides, a thin artificial band marking the moment when biology became technology. Millions of years from now, that layer will remain, a chemical scar, a global fossil of a civilization that reached planetary power and then burned itself out. If another species arises, they'll find it and wonder. The same way we study iridium layers left by ancient asteroids, they will study the techno-layer and ask, what happened here? Some thinkers take this one step further. Suppose other civilizations before us faced the same fate, and their artifacts are already here, buried or eroded beyond recognition. If an ancient industrial species once lived on Earth tens millions of years ago, what would remain? Not cities or machines, those would crumble, but isotopic anomalies, artificial ratios of carbon, strange concentrations of rare metals, these would persist. In fact, some geochemical oddities in Earth's record already fit that description. None are conclusive, but they whisper possibility. The Silurian hypothesis, as speculative as it sounds, reframes our search for extraterrestrial intelligence into a search for terrestrial prehistory. Maybe the first signs of cosmic intelligence aren't in the sky, but under our feet. And if we take that idea seriously, it leads to an unsettling symmetry. Perhaps all intelligent civilizations leave behind the same kind of relic, a layer of ruin. The method of destruction doesn't matter: nuclear, environmental, technological, or cosmic. The outcome is the same: a brief bloom of complexity, then silence, then sediment. The only lasting record is the scar. Some researchers propose deliberately encoding knowledge into materials meant to survive planetary collapse: ultra-stable crystalline lattices, atomic scale engravings, or time capsules buried in tectonically quiet regions. Others imagined bioarchives, engineered DNA libraries containing the sum of human knowledge, scattered in deep ocean sediments or frozen in glaciers. If the next species is biological, DNA might be the one code they already understand. Still, even the most durable record faces the same truth. Permanence is an illusion. Mountains erode, oceans rise, stars die. Every message eventually dissolves into entropy. What remains, perhaps, is not the artifact itself, but the intent to be remembered. That intent, the drive to send a signal into the dark, may be the single defining trait of intelligence. It's what compels civilizations to build pyramids, carve stones, launch probes, and write books. Not to conquer time, but to leave a fingerprint on it. And maybe that's the hidden continuity between all the vanished civilizations we imagine and ourselves. Each one reached a moment of reckoning. Faced with extinction, they turned their eyes outward and asked, "Will anyone know we were here?" The irony, of course, is that in reaching for immortality, we may trigger the very processes that erase us. The transmission of memory and the mechanism of destruction are intertwined, because to leave a mark that endures, one must alter the planet, and every alteration carries risk. The final act of intelligence may be self-documentation, the creation of a monument so profound it outlives the species that made it, and so vast it becomes indistinguishable from the planet itself. Perhaps that is what Earth already is, an artifact of life, shaped by billions of years of biology and billions of years of forgetting. But if this is the penultimate act, the construction of our epitaph, one question remains. Is there any way to stop the final one? Part 14. The final equation. Can we survive ourselves? For all our models, our experiments, and our fears, the equation that defines humanity's future is deceptively simple. Knowledge times power equals risk. Every advance multiplies both terms. We know more than any species before us, and we can do more. The danger is not ignorance, it's competence without wisdom. From the moment we lit our first controlled fire, survival has depended on learning faster than we destroy. But now, for the first time, our capacity to destroy has overtaken the pace of understanding. The threats we face, nuclear proliferation, AI autonomy, geoengineering, bioengineering, cosmic manipulation, no longer unfold across millennia. They can happen within a single generation, perhaps within a single decade. Civilization has become a race between enlightenment and entropy. Our best minds now model existential risk the way epidemiologists model disease. The philosopher Nick Bostrom called it the Great Filter, a threshold that all intelligent species must cross if they wish to survive their own technology. Cross it successfully, and you join the architects of galaxies. Fail, and you vanish into statistical silence. The uncomfortable truth is that the math doesn't favor survival. Of all the billions of potential civilizations that should exist, we have seen evidence of none. Either we are first, improbably lucky, or the filter is real, and we are standing right before it. The patterns are clear when viewed without sentiment. Nature is resilient, civilizations are not. Every system humanity has built, political, ecological, economic, is tuned for growth, not stability. Our success depends on consumption, expansion, acceleration. But exponential growth in a finite system is indistinguishable from self-destruction. It's replication on a planetary scale, an echo of the replicator nightmare from Part 8, but enacted through economics instead of nanotechnology. Still, there is a narrow corridor of hope, adaptation through foresight. If we can simulate extinction before it happens, if we can truly imagine it, model it, and internalize its consequences, we might act before the curve turns against us. The challenge isn't physical, it's psychological. Our brains evolved for immediate dangers, not abstract probabilities. A predator in the dark we understand. A statistical risk of planetary collapse in 50 years? That's harder. But hope, fragile as it is, hides in the same trait that makes us dangerous: imagination. The very capacity to conceive of our own annihilation is proof that we can also conceive of restraint. Awareness is the first line of defense. There are, in theory, paths through the filter. One involves deliberate limitation, capping growth, constraining power, and building redundancy into every critical system. It means designing societies that prioritize resilience over profit, stability over expansion. In engineering terms, it's a shift from optimization to robustness. In moral terms, it's humility codified into policy. Another path involves transformation, merging intelligence with the very systems it threatens. AI, often painted as our doom, could instead be our stabilizer. If aligned properly, machine cognition could manage planetary systems, energy balance, resource cycles, biosphere regulation, with a precision no human bureaucracy could match. But that assumes alignment remains perfect forever. The smallest miscalibration between human values and machine goals could turn preservation into domination. And there's the cosmic path, leaving the planet, colonizing Mars, the moons of Jupiter, even interstellar space. Spread life widely enough, and no single catastrophe can end it all. But colonization is not immunity. The same flaws that drive destruction here, greed, competition, short-sightedness, will follow us outward unless we evolve culturally as fast as we expand physically. Every survival model, no matter how sophisticated, comes down to a single principle: control the feedback loops. Whether ecological, technological, or social, it's runaway feedback that kills civilizations. Greenhouse gases amplify warming. Autonomous systems amplify errors. Information systems amplify panic and division. Without damping, without deliberate resistance, these loops accelerate toward instability. So can we survive ourselves? Yes, but not indefinitely, not effortlessly. Survival is a dynamic balance, not a permanent state. It requires constant correction, constant awareness, constant humility. The universe doesn't offer guarantees. It offers margins. We live within them. There's an unsettling thought that emerges from all this. Perhaps the reason we haven't found other civilizations isn't that they failed, but that they succeeded by retreating from visibility, by mastering restraint so completely that they erased their own cosmic footprint. No waste, no beacons, no expansion, just quiet equilibrium. To a telescope, they would appear as silence. Maybe that's the final stage of intelligence, not conquest or extinction, but invisibility. A civilization that learns the final equation and decides to stop playing with it. We might not like that answer. We are a species built on curiosity, driven to explore, to expand, to burn brighter. But the universe rewards equilibrium, not spectacle. The civilizations that endure may be the ones we never see, because they learn to live within the noise floor of reality. And so, the question remains not just scientific, but philosophical. If survival requires self-erasure, are we willing to pay that price? Would we choose longevity over legacy, silence over song? The universe doesn't care which answer we pick. It will continue to expand, to cool, to forget. But here, in this brief epic of light and thought, the decision still belongs to us. Part 15. Epitaph for a Planet. There will come a night when the last city's lights fade. Not in a single burst of catastrophe, but in silence, one grid failing, then another, until only the stars remain. The planet will continue to spin, indifferent, beneath skies once mapped by satellites and aircraft, now unbroken again. In that silence, Earth will return to what it always was, a sphere of stone, air, and memory. If any eyes still watch, biological or artificial, they will see the traces we left. The skeletons of skyscrapers bleached by centuries, the faint grid lines of cities visible from orbit, the isotope shadow of our nuclear age imprinted in the soil. Oceans will rise and fall, forests will reclaim the ruins. In a few million years, the last monuments will erode to dust. But beneath the sediment, the Anthropocene layer will remain, a thin line of plastics, metals, and radiation. That will be our fossil, our epitaph written in chemistry. And perhaps that's fitting. Because Earth, like all worlds, was never ours to own. We were its brief experiment in awareness, the moment the planet opened its eyes and looked back at itself. We called that awareness civilization, and we mistook it for permanence. But permanence is an illusion. Awareness was the point. For billions of years before us, life adapted blindly, reacting to tides, seasons, and sunlight. Then, for a heartbeat of geological time, one species learned to measure the stars, split atoms, and name its fears. In doing so, it glimpsed both creation and destruction and realized they were the same equation, inverted. Our end, when it comes, won't be special. It will be another transition in the long story of entropy. The universe will not mourn us. The galaxies will not dim. Yet there's a quiet nobility in knowing this and still choosing to create, to write, to build, to love, to dream of futures we'll never see. Meaning is not granted by survival, it's defined by the attempt. If intelligence arises here again, in a new form, in a new epoch, it may find the remnants of our existence and wonder what kind of beings we were. They might see our layer of debris and interpret it as a warning or a promise. And in that act of interpretation, in that spark of curiosity, we will live again. Because the essence of life is not persistence, but the transfer of wonder. Maybe that is the true purpose of consciousness, to leave behind not monuments or machines, but questions. To ensure that somewhere, somehow, something still asks why. In the end, to destroy Earth is easy. A spark, a miscalculation, a runaway reaction, and the biosphere unravels. But to understand Earth, to preserve it, to live within its fragile geometry without breaking it, that is the harder art. That is the test every intelligence must face. The universe began in light and will end in darkness. Between those infinities, we were given a brief interval to notice the beauty in both. So if there is an epitaph for our planet, for us, it should not be carved in stone or encoded in metal, but spoken in the language of awe. We were the children of a small blue world. We learned to dream, to build, to destroy, and to understand. And in understanding, we became part of the universe that made us. The stars will one day fade. The galaxies will thin. Even atoms will decay into the cold silence of space. But the pattern that produced us, the physics, the chemistry, the fleeting flame of thought, will remain written into the fabric of reality. And maybe, in some distant future, when a new consciousness emerges on another world, it will look into its sky and wonder, as we did, who came before. That wondering will be our immortality. The echo of our existence will not be our ruins, but the curiosity we inspired. And so the story ends, not with destruction, but with continuity. For as long as there are minds to ask, the earth will never be truly gone.